Good evening, all. Think I'm audible. Yeah. Yeah. Good evening, all. So myself, Sir Prasad. So to those of you who are listening to the lectures for the first time, so these sessions are actually help you to help understand and solve your assignment problems. These will be weekly sessions, and then we'll have for till the end of this particular course. And this week, these are the topics that we're going to be discussing on week 5 lecture videos. One is on polyhedrons and what are the different types of the conditions that are required to stay whether a given set of set of equations is to be called as a polyhedron. And then we'll discuss on what are the extreme points, rays, and we'll discuss the most important one called the Minkowski-Weil theorem. And that theorem will actually be used further to kind of reduce or simplify the way we represent a polyhedron. And then we'll discuss what is called a standard form for an LP problem. LP is a linear programming problem, and then we'll also use the theorem to see how can we find the optimal solution of an LP problem. These are the main topics. So maybe we'll wait for a couple of minutes for a few more students to join, and then we'll get started. Yeah, I guess we can get started. So these are the main topics that we'll be discussing this week. So let's get started with polyhedrons. So polyhedron is defined as an intersection of finitely many half spaces. So a half space is basically denoted by ax less than or equal to b. When you have a finite number of them, then and group all of them together, and the intersection of all those things is called a polyhedron. Obviously, each half space is a convex set. The intersection of convex sets is a convex set. So polyhedron is also a convex set. So mathematically, we represent in this particular way. So with this example, this we have discussed even in the last week. So circle is not a polyhedron because when you have a circle, in order to a circle, if you have a circle, in order to get a polyhedron, I have to write it in this form, ax less than or equal to b form. So if these are my coordinate axes, each coordinate axis will be a half space, for example, something like this. Or let's for now, let's take this. So one half space I can construct is something like this, some one tangent. So this entire region towards this side will be the part of the half space, and I can construct another thing, something like this, another tangent. So this intersection of these two spaces will be the entire region. That will also not be a polyhedron. So I have to keep on doing that. So I can draw so many tangents. I can keep drawing these tangents. You can keep drawing the tangents, but by giving, you always have certain area left always. In order to close it, you have to draw even more tangents. So you keep, ideally, you would be requiring infinite number of tangents to completely wrap this circle inside, inside these half spaces. So that would mean the important point here that it needs to be a finite thing is violated. So naturally, you cannot represent the circle in this particular form that we already know. So circle equation, if you write the circle equation, it will be x square plus y square less than or equal to r square, which is quadratic in nature. You cannot convert it into linear form. You can linearize it, but then it won't be a circle anymore. So this is what it would become eventually. So you'll have some error with respect to how you represent your domain or how you represent your feasible region when you convert them into the constraints or in terms of the polyhedrons. So this is what a polyhedron is. The next concept is the concept of extreme points. So when you have a convex set, the idea of a convex set is if you have any 2 points are there in that particular set, and if you take a linear combination of them, you get a resulting point, and the resulting point also belongs to the same set. Then you call this entire set to be convex set. So for example, if I have taken a set from say 0 to 1 on real number 9, so this is my R. On real line between 0 to 1, if I both included, or maybe we put it here, so put it here, both are included. So now what happens is if I take any point, any linear combination, provided some of the weight is for the linear combination is less than equal 0 less than lambda less than 1, then that should be equal, that particular x, the resulting x should also belong to the same set. So if I take any number here, take any lambda, take a weight combination of 0 and 1, the resulting number will obviously be less than 1 and greater than 0 since a lambda is positive. So it will fall in this set. So this is a convex set. Now what are the extreme points of the convex set is, the extreme points are basically those points which you cannot get a decomposition in terms of two different points. For example, if you take 0, I cannot get 0 in terms of any other point. The only way I can get to 0 is by doing a convex combination with 0 itself. And the same goes for 1 as well. I cannot get 1 from, like, in order to get 1, I have to take 1 point this side. If I'm taking a linear combination, I have to take 1 point here and 1 point outside the domain. That should not happen. For convex combination happen, all the points should be from within the same set. So eventually, you would eventually come back to the same point 1. So you should only do a combination with 1 and 1 to get to 1. These kind of points for which you cannot have, essentially you cannot decompose that point as a convex combination of two other distinct points from the same set, then those points are called the extreme points. It also makes intuitively sense that these are the boundary points, or these are extreme in the sense that you cannot decompose them. That's why they're called the extreme points. Now the idea if you extend the same idea, now here you have a bounded one. When you have a bounded set, you have extreme points. But what if you have an unbounded kind of things? That's where the concept of race and resistance direction will come. So you have the same convex set, but previously what we had said is we took a point. But now what we are saying, consider a vector D. So we consider a vector D such that, and you call a particular ray as, you take an arbitrary point x in S, and for each and every point in X, when you scale, go to a new point by x plus mu D, and that new point should also belong to the same S for all positive values of mu. Obviously for negative values, you can actually put a negative D and see whether you're fitting in that. Maybe I can give you an example. So if you can think of something like this. So this is a convex set, or maybe let me put this one. Just this, whatever is inside. This is extending in both directions. So this is going in this direction. This is going in this direction. So can I call this a convex set? So I take some point here, and I take another point here. I do a linear combination of both of this. Then whatever the resulting point will also be in the same set. I can take any points anywhere, and then eventually be the same thing. So this is a convex set. Now the question is, now we have to construct race in it. So if I take an arbitrary point, first I'll take an arbitrary point. Let this be an arbitrary point, and then I have to come up with a vector D. So I can take some arbitrary direction. Let's say I take this direction. If I take this direction and move this point, so what I'm doing here is moving from point x to x plus mu D. So that basically means I'm moving it to some new point here. So when I move here, and this should happen for any arbitrary value of arbitrary length of the vector. So if I keep on increasing this particular length, the point will eventually fall outside the set, which means this particular direction is not the vector that I want. So it basically doesn't belong to the set of rays. However, say if I take a direction like this, parallel to this particular one, how much ever far I go in this direction, I will always be in the same set. So such kind of directions are called the rays. So you can see naturally that this will eventually go and converge. So you can think of this as a cone. So if you have the origin in it, so say this is my origin, then you can see all this is very physical, intuitive also. You can think all these directions from which I can take an origin, I can scale it. You can take any point here and scale it along that particular direction. Eventually, all the points will belong to the center. Such kind of vectors are called the rays. Now this is for an unbounded thing. So when you have an unbounded thing, so as I said, like for every point you can take the particular vector from a ray set, from that particular set of rays, and then you can move along that particular direction by scaling with some mu, and then you will get up to some new point. This is the main concept in this. Now what can happen if you have a bounded set? Whenever you are bounded, it means that you cannot actually go beyond a certain point. Let's say I have a bound here. So there is a bound like this. The moment I have a bounds like this, then this particular arrow that I'm showing here cannot be a ray, because I can always scale it and then it will fall outside the domain. So whenever the set is bounded, so the moment we say that S is bounded, then the only vector that can satisfy this particular kind of scaling is origin. So then D will be origin. So the ray will be a set with just origin. That is for the case of bounded convex sets. The next concept is called the recession cone. So recession cone is basically defined, D is a ray of S. So it's a set of all vectors where that particular vector is a ray of particular set S. Then you call it the recession cone. The next is the concept of extreme. Just like extreme points, we have the concept of extreme rays. So if you take the same previous example for an unbounded set, or even let's say for an unbounded set, so this is what I had previously. So everything in this goes on infinitely in direction. Let's say it is unbounded. Now extreme ray is basically you have rays here. So all of these are rays. Just like points, you can do a linear combination of rays. So let's say I take two rays. I take one ray like this, and I take another ray like this. Now if I do a linear combination of this, then I'll get a new ray, something like this, right? So when I do a linear combination of rays, just like extreme points, extreme rays are those rays for which you cannot do a linear combination. So all you can do is just do a scaling. So basically again the same logic goes here. So you write that vector, you try to decompose it into two vectors, but you realize that you cannot do it in two distinct vectors, and eventually coming to one vector. And since like previously what we had is in case of extreme points, when we try to do, if you recall, in extreme points, we came to the conclusion that when you try to decompose into 2 points, both the points will actually be equal to the original point. So this is what an extreme point is. Now, because in extreme way we are dealing with vectors, so for a vector we don't have you can always scale it and get a new vector in the same direction. Direction is all that matters. Magnitude doesn't matter here. So instead of saying d equal to d1 equal to d2, we are just saying d equal to some alpha times d2. And this will be some say beta times d1 or something. So all you're doing is you can scale them and you can eventually get the extreme ray. So in this particular example, so the ray that is in this direction, beyond which you cannot go, so you can also intuitively understand it. So this is the if you take this as some kind of array, you start from this, you keep doing some linear combination, you eventually reach this point, and beyond this point you cannot get any ray. So this is an extreme ray. If you try to decompose it to some vectors, then you necessarily need some ray in this direction, and you would also require some other ray in a different direction, but that particular ray will not belong to the convex set because it is outside the feasible region. So the eventual conclusion you would come to is fall on this particular boundary. So these are extreme rays. And again, it is straightforward to say that this kind of extreme rays will happen only when rays exist. So which means if you have an unbounded set. When you have bounded sets, the only extreme ray you can have is origin. And origin is the only ray that you have. So you do not have for multiple values of extreme rays when you have bounded sets. You don't even have to have extreme ray concept when you have bounded sets. The next concept is Minkowski-Weil theorem. So here is where we discuss how to represent the polyhedron. So the theorem says that every polyhedron P is basically a set of points in Rn such that Ax less than or equal to P can be represented in the form P is the set of all x belongs to Rn such that x can be decomposed into two components. The first one is a linear combination of xk where k belongs to capital K, and capital K is basically the set of extreme points. And also summation of xr where xr belongs to and xr belongs to capital R where capital R are the extreme rays of P. So you have a particular convex set P, or you have a polyhedron P. In that polyhedron, you can decompose a polyhedron into a linear combination of into a convex combination of your extreme points as well as your extreme rays. Again, you can see here that we have sigma lambda k equal to 1, lambda k should be positive, and mu r greater than equal to 0. And I think I've not mentioned it here. Yeah. Another important thing is you need to have at least one extreme point. The particular k, the set of all extreme points, should not be an empty set. Yeah. So this is, what is this basically? What does this term signify? This we have discussed last week also. This is called a convex hull. And similarly, the next one is called a, what is this second one? This is basically the cone, right? This is how we define the cone. Cone is basically the set of all vectors. If you such that if you scale the vectors, the resulting vectors will also belong to the same set. Those are what we call as cones. So this is a convex hull and this is a cone. This is a convex hull of what? This is a convex hull formed by those extreme points, because xk are the extreme points, and these are the extreme rays. So it's the cone formed by the extreme rays. You can always scale the extreme rays and get back a scale version, but the scale version also belongs to the same set. So you can call that as a cone. So, so what this theorem essentially tells you is there is a different way, there is an alternate way to represent your, to essentially convey the same information about the polyhedron. So one way is to tell you in this particular way, saying that ax less than or equal to b. The other way to describe the same equation is if for example, if I tell you what all the extreme points are there, like lambda can be anything provided these constraints are satisfied. The only thing that is not known here is all these xk's and all these xr's. So another way to specify the same polyhedron is by specifying what the extreme points are and what the extreme rays are. So for example, if I have, so I have this some set like this. So so how do I represent this set? So this is 0, this is 1, 0, this is 1. So how do I represent this set? So this is basically x greater than or equal to 0, x less than or equal to 1, y greater than or equal to 0, y less than or equal to 1, right? So if I want to represent the set in the form of this ax less than or equal to b, so essentially my variables are x and y. My A matrix should have each 4 half spaces. So this will be a 4 rows and 2 columns. The first one is x greater than or equal to 0. So I can write it as ax less than or equal to b. So minus x less than or equal to 0. So here I will have again a 4 by 1 matrix. So the first one will be x less than or equal to 0. The second one will be x less than or equal to 1. So this will be 1, this will be 0, should be less than or equal to 1. The third one will be y greater than or equal to 0, and the last one will be y less than or equal to 1. So this is my A matrix, this is my X, and this is my B matrix. I can write it in this way. So all I can specify, the information to say that this is my feasible region can be represented in this particular way. You can specify the A value, you can specify the B value, and then the polyhedron is described completely. The other way to describe this is here you do not have any extreme rays. This is a bounded set. So this is my region that I want to specify. This is my bounded region. So I do not have any extreme rays. But what are my extreme points? So my extreme points are these points. Because if I try to express them, then I have to go in outside the domain. So these are my extreme points. So I can always say that these are my extreme points: 0, 0, 0, 1, 1, 0, and 1, 1. So if I say that these are my extreme points, and then I create a set by saying that the convex hull, this we discussed even last week, the convex hull of this particular set will be a square, right? So what we are doing is essentially the convex hull, the set of all the points that fall the, like, make a convex hull, and within the convex hull, whatever linear combination you do, all those points of x will actually belong to this, will actually get you back to the same domain, same feasible region. So you can either specify A and B, or you can say that take these 4 points, just with these 4 points you can construct the convex hull, and you can say what region is enclosed, and that should give you all the information which is equivalent to saying A and B. So this is the main crux of what Minkowski-Weld theorem says. So the most important point here I would like to highlight is why do we need this particular constraint? Why do we need k not equal to 5? Why do we need at least one point in the extreme set, like one point in the extreme points, at least one point? Because if you do not have an extreme point, which means you have something like a plane. If you have a hyperplane, say a hyperplane, when you have a hyperplane, what would happen? The moment you have a hyperplane, you do not have the extreme points because it's like a plane, your hyperplane, but then it is extending in all directions. Yeah, hi. Good evening. Yeah. Okay. So when we take a hyperplane, so it keeps going on in all the directions. So as it keeps going in all directions, you do not have any extreme points. So when you do not have an extreme point, so how do I represent this hyperplane? Like in this particular way, I cannot represent it in this particular way. Then I would end up having to represent the hyperplane in a different way. So that would eventually come to saying Ax equal to B form. Then it wouldn't fall under the category of polyhedrons, right? So we would require at least one point so that it will be easy for us to, when we have at least one point, then we can actually decompose it in this way. And we'll also see why this is important when when the linear programming problem is formulated and how we came up with the solution of how or why an extreme point will become an optimal solution. So this is a standard form of a linear programming problem. So you try to minimize a function. This is a linear function, C transpose x, subject to the constraint Ax equal to B, provided x is greater than or equal to 0. And this is these two for now. Let's not get into these two, but this should be sufficient for now. So you have to minimize some linear function subjected to these constraints. But usually the problem will be something like, so you want to minimize C transpose x. As we discussed before, you will be solving the problem in a feasible region. Your feasible region is a polyhedron. So that will be something like Ax less than or equal to B. So how did we get from here? Let's say this is form 1 and this is form 2. So how did we move from 2 to 1? You can go through the lecture videos as well. So the idea is pretty straightforward. So we do the transformation that we discussed in the last week. It's basically we transform this optimization problem in such a way that you actually end up here. So you can always, we discuss the concept of slack variables. So what we do here is add a new variable s such that it becomes like this, and then you say x greater than or equal to 0. But again, if you see the here constraint says all the x that come here should be positive, but here we are saying only s that's positive, which may not be true always. So which means I have to somehow transform this in another way so that all the variables involved in the optimization will always be positive. So what I do is I'll introduce something like x equals to some u minus v, where u comma v both are greater than or equal to 0. So depending on which one of them is larger, x can be positive, negative, whatever it is. But the moment I do this transformation, you can see how this comes up. So now when I try to minimize C transpose x, so this essentially becomes C transpose u minus v. I can write this as C transpose minus T transpose 0, something like this, right? If you multiply, this will be C transpose u minus T transpose v, and 0 times s will be 0. So that is this. And similarly, I can write the next one. I can transform the next one. So all I have is a into u minus v plus s equal to b. So this also I can transform in a similar way. So let's say I write it as a minus a, and this is 1. This is basically 1 in the sense this will be an identity matrix or the column of, so that it will match dimensions of s into something like this. So what did I do here? So this entire thing I am calling some a new a, and this entire thing I can call it as x equal to b. Similarly, this entire thing I can call some new c transpose, and this entire thing I can call x. So you can see how this problem has transformed now into the same that we were saying. So you have minimized c transpose x subject to the condition ax equal to b, and you have also have the condition that u v greater than equal to 0 and also s greater than equal to 0. That essentially means x is greater than equal to 0. So all the three things come into picture. Again, as we said, like for this to be feasible, we need to have A to be a full row rank. Obviously, if it is not full row rank, you can always reduce it. You can do some row manipulation and kind of make it full, like eliminate the rows. You can make the particular values of B0, so you can reduce the redundant equations, and eventually it will become a full row rank. So essentially, it means like you don't keep any redundant equations in the problem, and then you have the constraint be positive. Like essentially, that is just a way. Standard form is that in order to see that whoever solves the problem, they should always end up in the same one. So you can either take, for example, the values here. I can always multiply this, take the minus sign here. So if b is positive, I can leave the mathematics. If b is negative, I can always multiply that with -1 and get the same equations. Since this is an equality, so I can always multiply. So that in order to ensure the standard thing, what we do is just ensure that b is positive. So if b is positive, then everyone will get the same gain. So that's the kind of form in which it will go and be used in certain solvers. Okay. Are there any questions in this up until here? I don't think there are any questions. Okay, so now we have formulated the problem. The question is, how do you find the solution of it? So what is the solution of this problem? So if P is a polyhedron, so this is a theorem that says that if P is a polyhedron with at least one extreme point, if it has at least one extreme point, consider the LP, the linear programming problem, in the standard form, and suppose the optimal value is finite. So we are assuming, again, in the first week of lectures, we discussed that existence is the first criteria that needs to be satisfied. Only if some optimal exists, if we know that it exists, then we can go and try to solve it in some way. So we discussed on uniqueness theorem, so we discussed on existence theorems and all that stuff. But for now, we're assuming we also came up with the first order, second order, first order sufficient conditions and necessary conditions, which are kind of says that if the solution exists, this is a condition that it should satisfy. In a similar way, this is also goes in the same lines. So if you are assuming that an optimal value exists, so that if existence, we are not going into whether it exists or not. If it exists, then at least one extreme point of B is an optimal solution of the LP. So if the optimal solution exists, if the optimum exists, then one of the extreme points of your whatever feasible reason you have decomposed it into the polyhedron. The polyhedron you constructed, in that polyhedron you will have at least one extreme point, and that extreme point will be your optimal solution. That is what this particular theorem says. Yeah, you can also have multiple optimal solutions, but multiple optimal solutions in the sense that when we are trying to do is minimize C transpose X by varying X. So you can have multiple optimal solutions. You can have X star, Y star, so and so. All of these will, or let's put subscript here, X1 star, X2 star, whatever. All of these will be there. You can have multiple solutions. You can have multiple solutions, but all of them will be extreme points. And then it also says that you can have multiple solutions, but not all of them can be extreme solutions. All it says is at least one extreme point will be an optimal solution. So if you have so these are my extreme points, say. Maybe this is an optimal solution. Maybe there is some other point x1 star which doesn't belong to the set here. And that could also be an optimal solution. That could also be an optimal solution. We are not talking about that point. So there can be points which are not extreme points and still be optimal solutions. But what we are saying is, if it is an extreme point, out of all the extreme points, there will be at least one extreme point which is a solution to this LP problem. And whichever extreme point you use, either you choose points from the extreme point or you choose from something which does not belong to the extreme point, but the optimal value that you're going to get, that is once you do C transpose X star or you do C transpose X2, both of them will be equal. So the objective value will remain the same, but the value of X might be different. So that is what this particular point says. In the extreme points of the standard form, like once you have the extreme points, then they are called the basic feasible solutions. Now the problem boils down to this. So I have my LP problem. So you have given me what the polyhedron is. You have specified Ax less than or equal to B. But in order to find the optimal solution, I need to find the extreme points. Once I have the extreme point, I can calculate the objective function in each and every extreme point, and I'll see which of them is the minimum value. So, but then how many extreme points can I have? For a given polyhedron, Ax less than or equal to B, let's say X is an M by N matrix, X is n by N by 1, and B is also N by 1. So I have something like this. So for a polyhedron like this, how many extreme points will I have? We will solve some problems on this also at some point later in the class. For now, we just ponder over it. So how do we calculate the number of extreme points that this particular system can have? So for example, if I have a square kind of thing, how many extreme points do I have? Like square, if I have square that we have discussed before, it's basically 4 by 2 system. A is a 4 by 2 system. With a 4 by 2 system, I have 4 extreme points, right? In order to represent a square, I have 4 lines, and then I will require at least 4. I'll have 4 extreme points. So if I have a hexagon, how many extreme points do I have? How does it relate with that? So if I have an hexagon, then I have to have 6 particular half spaces, like it's an intersection of 6 lines, and the extreme points is also 6. So how does it matter? So can I say that this will always be equal to m, or does it have something else? So if I take a square, I have 4. If I take a hexagon, I have 6. So can I say m? It's actually no. You can ponder over it for some time, and then I'll again get back to this when we solve the problems, and you can tell me your answer. Yeah, the next is the concept of basic feasible solutions. Just as I said, whatever the values of extreme points you have, those are called the basic solutions. So the idea is very simple. So you have the trick here. So the matrix A, B, M cross N can always be decomposed into 2 matrices. One is an M by M matrix, and the other one is an M and remaining elements, whatever, N minus M matrix. Now when I write Ax equal to B, I can decompose A as Bn, and I can also write it as Xbxn. So this eventually will give me Bxb plus Nx equal to B. So what we are trying to do here is Ax equal to B, if it is a square matrix, I can always do an inverse and calculate the values of x. And those x I can see whether x greater than equal to 0 is satisfied or not, and that will be my solution. But now, if A is a rectangular matrix with the number of rows less than number of columns, then obviously I have more unknowns than the number of equations. So what I can do is I have to set some of those unknowns to 0. That's the only way I can find the remaining unknowns. So what we do is here we split it into xp and xn. So xp is basically out of those variables, we are choosing m variables. This will be m variables, and this will be the remaining n minus m variables. So we are setting n minus m variables to 0 and solving for the remaining m variables. Then we'll get some values of x. So that values of x is b inverse b. And we are calling this particular thing a basic feasible solution only if xp is greater than or equal to 0. So what do we mean xp greater than or equal to 0 is because we have the original constraint in our, like when we formulated the problem, we formulated saying that the x should be positive or x should be non-negative. So only then it will fall inside the feasible region. So this is extra thing that has to satisfy. So now how many combinations do I have here? So I have n variables, out of which I can choose m variables. I can always choose m variables out of these n variables. So this can give you kind of the permutations that you will be doing maybe in your +1 or +2, or maybe even in your high school. So the entire problem has boiled down to this: how many combinations of x I can make 0. So out of n, This is again straightforward, right? So you have n variables, out of which you can always choose n minus m variables. Obviously, from combinatorial law, you always have ncn minus m equal to ncm. So this is the number of combinations in which you can make a certain set of variables to 0, and that will tell you how much you can, how many variables you can, like how many different feasible solutions you have. So you can always take one entry out of all these elements, and that will give you one value of xp. That is one basic feasible solution. Again, you can take the second one and get the next one. So you can keep doing this. So this will be the number of basic solutions. This is like maximum number of, we just call it BFS. Yeah. Okay. Before going to problems, you have any questions until now? Yeah, I think there are no queries. Okay, then we'll get started with the problems. Okay, the first one is you have a particular set defined in this particular way. A set belongs to R2, so it is in 2D, such that mod x1 plus mod x2 less than or equal to 1. Is it a polytope? Again, what is a polytope? A polytope is basically a bounded polyhedron. So how do I solve this problem? So this is basically, so there are two things that needs to be qualified to call it as a polytope. One is it should be a polyhedron. The other one, it should be bounded. So how do I know? How do I know whether these two conditions are satisfied or not? So let's take this equation. So for it to be a polyhedron, it should be able to be written in this form, ax less than or equal to b. So let us try to write it in this form. So x is basically x1 and x2. In the set of equations given by mod x1 plus mod x2 less than or equal to 1, they'll be essentially be both being positive. This is negative. The other one is positive, and vice versa. And you have all of them to be negative. So these are the set of 4 equations. So if I write it in the matrix form, so my matrix A will be 1, 1, minus 1, 1, 1 minus 1, and minus 1 minus 1. This is my P. So I have 4 rows, 2 columns. This is my A, this is my X. Sorry. This is less than or equal to my B. So I was able to write this in this particular form. So this means this particular equation, this set of equations, or this particular set which is given by these equations is a polyhedron. So now how do I know that it is bounded? See, remember, how do we say boundedness? So one way you can say is you take a particular point, you try to do a convex combination of those points, and if the resulting point also falls in the same set, it is anyway a convex set. So for boundedness to be true or false, all we can check is check for race, right? That is, you take some point x, and then you take x plus mu d, and if this x plus mu d also belongs to the same value of into the same set for any value of mu, for all mu, take a point x and you get the new point. For all mu, if this, let's say mu positive, if this particular thing happens, then the set is unbounded, right? But however, if for only specific values of mu, if this particular thing is true, then I can say it is a bounded set, right? Do you agree in this? So if I take this particular equation, so if I take a point x and then I do x plus mu d, so that will be x1 plus mu d plus x2 less than or equal to 1. From this, if I take mu should be less than or equal to 1 minus x1 plus x2. Sorry, okay. I have to take some particular vector d, so let's take d as 1 0. If that is my vector, so this will be just mu. So mu should be less than or equal to this. So, and it should be greater than 0. So you can see that there is a certain restriction on mu. I cannot possibly take all values of mu. Hi, good evening. Yeah. Okay. So you can there is a restriction on the values of mu. The moment when we have a restriction on the value of mu, it would only mean that I cannot take any arbitrary mu. So the only ray that can possibly be is just the horizon. So which means it is not bounded in any sense. So sorry, if I can take any mu, then it is unbounded. But there is a restriction on mu, which only means that the set S is bounded. Right. So I have checked the polyhedron. It is a polyhedron and it is also bounded. So since both the conditions are satisfied, I can call it a polytope. Instead of doing all these things, you can always, okay, since it is in 2D, it's quite easy. You can just take a plot of it. If you just plot, so it would be something like this. This is my 1 minus 1, 1 minus 1. So, and since it is less than, so this will be the entire region that is inside this one. Yeah, you can see that it is bounded. It is bounded and it is a polyhedron. So you can always call it a polytope. Yeah, but this, since it is 2D, it is quite easy to see and visualize. But usually you'll have say 100 and 200 equations or say million equations, and it will not be possible in this way. So all you have to check for is in this particular version. Yeah, maybe you can solve this problem. This is actually pretty straightforward. Again, if you check for, you should be able to write it in the form ax less than or equal to b. But for this is a linear equation. But as has quadratic terms. S is basically a circle, so it is not a polyhedron. Since it is not a polyhedron, it's not a polytope, right? Straightforward. Now let's take this one. So we have a particular set S in 2D such that x2 equal to mod x1. Is this a cone? So what is the definition of a cone? Cone is basically the set of all vectors taken such that if you scale that particular vector, some lambda times d should also belong to the same set for any value of lambda you choose. Or let us just restrict to lambda greater than or equal to 0. So if lambda is less than 0, essentially that means you take the negative value of a, and that would also belong to the same set. So you can, this is basically my cone. Is this set a cone? So how do I do that? So this is an R2. So I have to first construct a vector d. So the vector d will be some x comma y. So this is my vector. So just putting transpose here, or let's just use a column notation, column vector. So I'm saying that d belongs to this particular set. So which means I'm saying d belongs to it. So the relation between these two should hold. So y should be equal to mod x. So it should be something like this, right? D belongs to x implies y equal to mod x. Now what I have to do to check whether it is a cone or not, I have to multiply it with lambda. So if you take lambda d, so lambda d will be lambda x into mod lambda times mod x, and the condition is lambda should be greater than or equal to 0. So if lambda is greater than or equal to 0, I can always take it as lambda x and mod lambda x, right? Again, you can see that this, if I call this as some x prime, if I call this as some y prime, then I have y prime equal to mod x prime, right? So which means lambda d also belongs to the same set S. So I've taken some arbitrary vector belonging to the particular set and I've scaled it with lambda, and I got to the conclusion that the scale vector also belongs to the same set. And this is true as long as lambda is greater than or equal to 0. That is the constraint that we have. That is how we define the cone. So S is a cone. Are there any questions? Now let's take this particular set. So x2 equal to x1 instead of mod, let's take x2 equal to x1. Or if okay, just to put it in a geometrical sense, how would this look in 2D plane? This is my x1 axis. This is my x2 axis. X2 is mod x1, so you have something like this. Again, point here is x2 equal to mod x1, so it's only the points on this particular lines. It has nothing to do with anything in between, just the points on these lines. If you take any vector along those lines and scale it, that will also belong to the same set. Again, you take any vector on this line, scale it, it will belong to the same set. So this particular set of points on this line, what are all the points on this line? This line will extend to infinity. It won't come downside since it's mod x1. So all these points on this particular line will actually form the set, form this particular set cone. So maybe I should ask one more question. Is S convex? No, right? You can see that pretty clearly. So you can take any 2 points. Let's say I'll take some point here, let's take some point here. And if I do a linear combination of these 2 points, then I'll get some point in between, some points on this particular line, which do not belong to the set original set S. So this is not convex. Right? Okay. Now let's take this problem. So you have a set yes, x belongs to R2 such that x2 equal to x1. Which of the following is the recession cone of yes? So what is the recession cone? We have discussed this before. See, a recession cone is basically the set of all vectors such that the vector is a ray of particular set yes, right? Array is basically the vector, so that if you take any point in the set yes, and if you move along the particular vector, you should also end up in the same set. Then you call that vector as array, and the set of all those vectors is called a recession cone. So is this, first let's understand this. So in R2, if you have this, just go on instantly. So all the points on this particular line, x2 equal to x1, so say this is x1, say this is x2. All the points on this particular line are is what my set is. So if I construct a vector d, so the vector d would be something like, so what should be the vector? The vector could be something like this or something in this direction, only one of these two directions. Then if I take any point and scale along the direction, so only if my vector d is one or let's say some lambda. So only when both these are equal, for those kind of vectors, I can always take a point on this one. So let's take a point x1, x2. And I want to move to a new point. So that will be x1 plus mu times the vector lambda and x2 plus mu times the vector lambda. So now what happens is this particular quantity is equal to this particular quantity because x1 equal to, since this belongs to the set yes, this implies x1 is equals to x2. So this equal to both these components will also be equal. So this particular set will also belong to the same set yes. So I've taken a point and have scaled it and moved it in the direction of some arbitrary vector d. So then d is in this particular d. So which, and then I got a new point, and this new point also belongs to the same set yes. So by the definition, d is array, and the set of all d's is a recession cone, and that set is this. So if I define my recession cone as basically uh, something like this, where lambda is positive, right? And this forms my recession cone. So I have to check these points if they are satisfying this particular constraint or not. So this satisfies, and remaining everything doesn't satisfy, right? So lambda doesn't have to be positive, can be negative as well. Lambda just belongs to some real number. It can be negative because you can also move in a different direction because we have a restriction on mu. Mu should be positive. If I do not have a restriction on mu, then lambda can be positive. But now I had a restriction on mu, which means lambda can be positive or negative. Yeah. So yeah, so this satisfies both to be equal, and the remaining do not satisfy. Yeah. Are there any questions, or is it clear? Yeah. No questions. Okay. Yeah. Now let's get to LP problems. So you have an LP problem defined like this. So you have two variables x1 and x2, and I have to minimize 5x1 plus 6x2 subjected to these constraints. So again, this if you write in the matrix form that we are quite used to by now, so the form will go something like minimize x is my vector, and this will be C transpose x subject to, so if I write it in this way, or so that just to be comfortable, so I'll just write the standard form, so not the standard form, C transpose x, that this is the general form A x less than equal to b, and you have x greater than equal to 0 in this particular way. If I want to represent in this particular way, C is basically 5 and 6, x is basically x1 and x2, my A will be, and B will be. Oh, we do not have this in the original form, right? So it should be Ax less than or equal to B. So my A matrix and B matrix should be expanded now. They will also have the other terms. This will be minus 1, 0, 0, minus 1. And we'll have those here, right? So I can write all this entire equations in this particular form with these particular matrices. That will be mu C transpose X such that Ax less than or equal to B. So this is my polyhedron and this is my objective function. So the polyhedron will represent your feasible region and I have to minimize this objective function in that feasible region. So this is clear. So the question asks you, how many additional variables are required to convert the above problem in the standard form of LP? So how do we convert this into the standard form? So previously we discussed this. We have this original problem and from this problem we somehow from this we converted into, yeah, of course the C here and C here are different. A, B, C, A, everything is different. But you can convert from one form to another. They are interchangeable. We did this even last week. So just now in the derivation we discussed this one. So how did we do that? So essentially we decomposed it into ways such that we wrote x equal to u minus v and then we wrote ax plus s equal to b. So we introduced three additional variables u, v, s such that all of them are positive, right? With those things we were able to solve the problem. But now if you see, we have two quantities u and v, so essentially both of them positive, but here we already have the constraint that x is positive. So you don't need two quantities. We know that only one of them is going to be true. So which means you only need, since x is greater than or equal to 0, this implies only u or v is, only u is needed. So in my new transformation, all I would be needing is u and s. So what would be the dimension of u? The dimension of u would be the same as the dimension of x. So I would just require u and s. And the dimension of u will be the dimension of x. And s will be the dimension of a minus, or maybe see, if you see the s here, ax plus s equal to b. So s dimension should be same as the dimension of b, right? So how many additional variables are required? So u is basically equal to my x. So x is equal to u. So the additional variables will be s. Then the dimension of s is equal to dimension of b, which means I require, in the original problem, so if I have to convert it into the standard form, I can write it as minimize this subject to x1 plus x2 plus s1 equal to 1, x1 plus 2x2 plus s2 equals to 2, and then I have the constraints x1 greater than equal to 0, x2 greater than equal to 0, s1 greater than equal to 0, and s2 greater than equal to 0. So now we can see this. So this extra things I can remove here because they're already there in the standard form. Okay. This is in the original form, but when I convert it into standard form, I always have x greater than equal to 0. So this is my x. These are my ax equal to b, and this is my c transpose x. So you can see this is in the standard form. So how many extra variables I've added? Only two extra variables I've added. One is s1, the other one is s2. This is clear. So how do we determine it? So essentially, if you convert all the inequalities into equalities, so the number of inequality constraints will be equal to the number of extra variables that need to be added so that you can convert all of them into equality constraints, right? Because equality, once we have the equality constraint, then we will be able to solve the problem. We'll assume some of the unknowns to be 0, and then we'll go ahead and solve the problem. That is what we discuss in case of the basic feasible solutions, right? Yeah, I'll pause for a minute here. If there are any questions? Yeah, okay. So again, the same problem, but then the only difference now here is instead of inequality constraints, you have the set of equality constraints. So how many additional variables do you require to convert this into standard form? So if you compare this with the standard form, so I already have it in the standard form, right? So the standard form is something like minimize C transpose X, Ax equal to B, X greater than equal to 0. So here C is my 5, 6, X is my X1, X2, A is my, right? So it is already in the standard form, so which means I do not require any additional variables. Okay, is this part clear? Yeah, this is actually quite straightforward, so I don't think anyone has any doubts in this. Okay. Next one. If the feasible reason of an LP is an unbounded one, the optimal value of the LP is also unbounded. Is this statement true or false? So what we discussed previously when we discussed Minkowski-Bell theorem, and further we discussed on what will be the optimal solution, is at least one of the extreme points this is what we said. So now, and if it exists, is based on the assumption that if it exists. So if a solution exists, then at least one of the extreme points of that particular feasible reason will be my optimal solution. That is what we told before. So, so from using this statement, we can comment anything about this only if we can say whether, so if you answer the question, say, can an unbounded polyhedron so if you take an unbounded polyhedron, can it have any finite number of extreme points? Can you think of any scenario where you have an unbounded polyhedron and have finite number of extreme points? It's very straightforward, right? You can take something like this, some nozzle kind of thing. This is my set if this keeps going on in this direction. This is unbounded definitely because it keeps going, you can always have the race. So it is unbounded, and still you have the extreme points here. So these are my extreme points. So there are certain, there can be unbounded polyhedrons which have a certain number of, finite number of extreme points, which means if a finite optimal exists, then it can be one of these extremum points. So just because an LP problem is unbounded doesn't mean it doesn't have an optimal value. The optimal value can still be bounded as long as you have certain finite number of extreme points, right? Is this clear? Are there any questions in this? Right? No problem, right? Okay, next one. So consider a following LP problem where you have to minimize the same thing in the standard form, minimize C transpose X, thus that Ax equal to B and X greater than equal to 0. Suppose you have two optimal solutions. Let's say you have two optimal solutions X star and Y star for the above problem. Then any convex combination of X star and Y star is also an optimal solution. Is the statement true or false? Yeah. Oh, so how do you solve this? You have two optimal solutions and then you take a linear combination of them. Will it also be an optimal solution? How do I check it? So see, obviously the first one is it is an optimal solution. So Ax star should be equal to B and X star should be positive. Similarly, Y star is also an optimal solution, so it should be feasible. And as we discussed before, since both are optimal solutions, and which means the objective value should be same for both of them. So C transpose X star should be equal to C transpose Y star. So if I define a new point just as a linear combination of these 2 points, so lambda X star plus 1 minus lambda into Y star, such that you have the condition satisfied, then what would happen? So first thing, will it be an optimal solution? So what would be the, so will it satisfy the problem A z equal to, will it satisfy the constraint? So clearly, since X star and Y star are positive and lambda is a positive quantity, so first let's say X star is positive, Y star is positive. So let me put some numbers. And this is 6. So you can see from 2, 4, and 6, it follows that Z should be positive. If both of these are positive quantities and then you're just doing some weight summation with another positive quantity, so obviously the summation will also be a positive quantity. So Z is greater than 0. If you have the equality, then you have greater than or equal to 0. If both of them are 0, then it can be 0. Then now let's say what about this AZ? What can I say about AZ? AZ I can write it as star plus 1 minus lambda Y star, and this will give me lambda times AX star plus 1 minus lambda times AY star. This is giving me what? Lambda times B plus 1 minus lambda times B. This is again B, right? So I have AZ equal to B. So it satisfies the constraint, that linear combination satisfying that particular constraint. You don't have to do all of this. You can directly say that Ax equal to B is a convex set. So if you have a convex set, you take a convex combination of 2 points in the convex set, then we'll always end up in the same point. That is what we have proved till now, up until now. There is nothing new in this. So how do we say that this is the same optimal solution? So you calculate the objective value. So that is C transpose Z. That will be C transpose lambda x star plus 1 minus lambda y star. And this will give you, with this objective value, we call it as say, gamma. So this will be lambda times C transpose x star is gamma plus 1 minus lambda times C transpose y star is also gamma. So that will give you gamma. So there is the same objective as equation 5. So the particular point, the convex combination, since it is a convex combination, it will also lie in the convex. So that is clear. But if you calculate the objective function, just because it is linear, because we have a linear objective function, it's and we are doing a linear combination, the objective function value also doesn't change. So it will be the same value. So Z will also be an optimal value. So I can say Z is equal to Z star, or I can say Z star equal to some Z. The actual value of Z star can be different from X star and Y star, but the objective value will remain same and it will satisfy all the constraints. So which means it is also an optimal solution. So any convex combination of optimal solutions will also be an optimal solution. That is happening just because of the linearity provided in the objective function. If the objective function is non-linear, then it may not happen always. Right? Is this clear? Yeah, I think it is clear. Okay, now this is where we discuss like how many possible solutions do you have. So you have set of equations, system of equations Ax equal to b. X belongs to R6, which means you have six. It's a 6 number of rows. It's a column vector with 6 rows. A is a matrix with 4 rows and 6 columns, and B is a vector with 4 components. So if X prime is defined as so and so, then X prime is a possible basic solution, or it's a basic feasible solution. Can I call it as that? Can X be a possible solution? Yeah, I don't know the values of A and B, so I cannot say whether it will be a basic feasible solution or not. But can it be possible? Can this particular value of X can it be a basic possible basic solution? How do we say that? Whether there is a possibility or not? So what are the main criteria for your basic feasible solutions? So in order to be a basic solution, it should be one of the extreme points. That is one of them. Or to put it simply, we have Ax equal to b. For it to be a basic solution, so if you remember, we decompose this matrix into 2 components. And this is where the trick comes, right? So we have to solve it. And we made this xn equal to 0. So this is the main criteria, right? So your x is basically should be of the form xp and 0. Then this xp is your basic solution. Or this entire x is your basic solution. But this is how the form of this should be, right? If x is of this particular form, essentially this what will be the dimension of xp? You have m rows here. So if A is an m by n matrix, I have m rows. So x will be an n by 1. So out of this will be m rows and this will be the remaining n minus m rows, right? So I need to have n minus m zeros at least in this vector. I mean, even in xp you can have zeros, but that we are not talking about those zeros. But this n minus m should definitely be 0. Only then I can convert it into this form. I can make this 0. I can solve for xp. Only then I can solve for xp equal to some b inverse b or something of that sort, right? So in order to do this, I need to have b to be invertible. But for now, let's say b is invertible. This b is invertible. At least I will rearrange so that I'll have only the linear independent rows, and I choose only them to be my basis. So the main criteria is you need to have n minus m zeros here. So here, what is the value of m? M is 4, and you have n is 6. So with this combination, n minus m will be 2. So the last 2 rows of x should be 0. But here, if you see, this is 2. This is not equal to 0, which means this cannot be a positive basic solution, right? You don't like unless I give you the values of A and B, you won't be able to tell me whether this is a basic feasible solution or not. Because for it to be basic feasible solution, it has to satisfy the equation Ax equal to B. Without knowing A and B, you can't comment anything on that. But we can say that this cannot in any way be feasible solution because we have a non-zero value here. Is this part clear? Yeah, I think it is clear. Okay. So the next one is also some similar question, but then instead of asking you whether it is feasible or not, we are asking how many maximum number of basic solutions you have if the system of equation is of this particular way, where you have x belonging to an R10 and A is a matrix with 3 rows and 10 columns. So A is a matrix with 3 rows and 10 columns. X is a matrix with 10 rows and 1 column, and that is equal to P, which is something like this. So how many possibilities can I have? So as I said before, in order for this to work out, since there are only 3 rows, the first 3 elements should form, and the remaining 7 elements, this should be zeros, right? This is the general structure of your basic solution. So how many possibilities can I have? So out of 10 variables, I can make any 7 of them to be 0, right? Depending on which 7 you choose, your combination changes. So if you choose by changing the sets from different 7 values, you get different values. So I can have 10C7 combinations, or I can put it in different way, 10C3 combinations. So that will be this we have discussed before also. So this is basically NC n minus n, or you can call it NCN. This many basic solutions we have. So now you see the problem here. So for example, we told before that all these basic solutions are basically your extreme points, right? So you have this many extreme points. So you have 120 extreme points. So at each of these extreme points, like from the Minkowski-Weyl theorem, like after using the Minkowski-Weyl theorem, we came to the conclusion that one of these extreme points will definitely be an optimal solution. So if I have this particular kind of a system, then I have to solve all these 120 equations. Then I'll have 120 different points, and out of those 120 points, at least one point will be the optimal solution. So previously, how many points I have to search for the entire domain? I can split the entire domain into some grid points and then solve at each point. Is that all we came to the conclusion is from infinite number of points in the entire R10, we reduced to this 120 points. So now all we have to do is out of these 120 points, we need to find the correct value. Which one is the optimal value? Again, we will see how we can reduce this number 120 further down. What can we use to reduce the number further down from 120? Is there any fact that we left behind that can actually be used to reduce this? These are the things that we'll discuss in maybe upcoming lectures. But for now, you can understand just by introducing the concept of polyhedron and convex sets. And this is just possible because it is a polyhedron and it is a linear objective function. We have a linear only with these considerations, when you have a feasible region as a polyhedron and when you have a linear objective function, and that is in the specific case of linear programming problem, we have used these two facts to reduce the search space from infinite dimensional just to these 120 points, right? That's why we are learning all of these things. So instead of doing it some brute force search every point, see whether it is optimal or not, we are somehow finding some smart ways to reduce the number of points that we have to search for, right? Okay. Yeah. So the last question I have for this week. So you have a following system of equations with A and B given here. Which of the following is a basic solution? So again, if we just stick to the same value, so I have 2 rows, 3 columns. So my x should be something. So how many zeros should I have? Since this is 2, so I should have at least n minus m, that is 3 minus 2. So at least 1 0 should be there. Yeah, of course I can rearrange the rows. You see, this is just the equation, so you can always rearrange them. So you can see I have a 0 here, so this could be a potential one. I have 0 here, so all you can do is you can rearrange them, then you can interchange the rows and you can interchange the columns and you can get the same value. This is also a possible candidate. This cannot be because there is no 0, so this cannot be. Again, this is 0, so you can, this can possibly be. So all we are doing is checking for this condition. So let's say this is condition 1. According to condition 1, they are okay. What is the next criteria for it to be a basic solution? Next criteria is it should satisfy x equal to b, right? So you have a, you have x, you can see whether it satisfies the condition. So let's say if you take the first one. So if I take the first one, so I'm getting satisfies the condition, right? This is my second criteria. It has to satisfy x equal to b. So if I take the second point, that also satisfies the constraint. But take the last point, this doesn't satisfy the constraint, right? So these 2 points are the basic solutions. It has to satisfy x equal to b, and you have the other constraint that x should be positive. So everything is positive here. In all the 3, all are positive. So maybe I can put that as the third condition. The third condition is basically saying x should be positive. Yeah, but yeah, so basically this, so ultimately it should satisfy x equal to b and should have x greater than equal to 0. This, the first one is, it will naturally satisfy anyways. Once you have x equal to b, the other one should be 0. That otherwise this equation won't be able, you won't be able to solve the equation. So with these 3 conditions, you are able to satisfy, know whether this one of the solutions is a basic solution or not. Are there any questions in this? Yeah, these are the questions I have for this week. So let's do a quick recap of what we discussed during this week. So we discussed what a polyhedron is. So essentially, these are the sets which you can describe in the way by intersection of half spaces. So it should be written in the form ax less than equal to b. And then we discussed what is called an extreme point. So these are the points in the set which, if you try to decompose into a convex combination of 2 other points, then you will end up having the same point. So you cannot decompose these points into 2 distinct points. So those are your extreme points. And we defined what a ray is. A ray is a particular vector, just that if you take a point in the convex set and you go along the, you can scale along that particular direction along the particular vector and go to a new point. If the new point also belongs to the same set, then that particular vector is called a ray. And the set of all those rays will form, since it is a set of vectors, it will form a cone, and that is called the recession cone. The next theorem is the Minkowski-Weyl theorem. So that says basically when you have a polyhedron which is in the form ax less than or equal to b, you can always decompose it into a set of, into a convex combination of something like this, where you have xk, which is your extreme points, and then you have xr, which are your rays, extreme rays. So you can always decompose your, you can always express the same convex set, which is in the form ax less than or equal to b, or intersection of half spaces, in terms of extreme points and extreme rays. You just, if you list down the extreme points, extreme rays, then make a cone out of the extreme rays and make a convex hull out of the extreme points, then that enclosed region will be same as the will be same as this one, ax less than or equal to b. That is what the Minkowski-Weyl theorem is. And then we discussed on the optimal, what is the standard form of linear program. So the original program, which is minimized T transpose x, ax less than or equal to b, can be converted into this form, and both these forms are equivalent. Of course, the values of c here and here will be different. They will be mapped in this particular way. Again, a and a will be different. So the a here is this one, and the a here will be this particular one here. And similarly, x will also be changed. X will be some vector here. But this is the standard form. And this is just to ensure that when you code it or something, all the problems can be converted to standard problems. You can, instead of writing codes for different scenarios, you write the code just for the standard form. And when you give the input, you give the input in the standard form so that the code works for all the scenarios. Yeah. So, and then we discussed how to find an optimal solution for this. This theorem only states that if you have finite number of extreme points, then at least one of them will be an optimal solution. Of course, you can have multiple optimal solutions, but whatever be the optimal solution, all of them will have the same objective value. And these extreme points which satisfy, of course, extreme points will belong to the feasible region because they belong to the convex set. And since they belong to the feasible region, and one of them is an extreme, they are called the basic feasible solutions. So out of all these feasible solutions, why are we calling, like you can have 100 different, all the points in the interior will satisfy the constraints, right? Ax less than or equal to b will be satisfied by all the points inside the polyhedron. But we are only taking the extreme points because we know one of them is going to be the optimal solution. So from an infinite number of, instead of searching for infinite number of points, we now reduce the problem to just solving for the uh, finding the optimal solution out of the basic feasible solutions, where these basic feasible solutions will be equal in number to the number of ways you can get zeros out of the entire thing. So that is what we discussed in the next one. So we decompose the matrix into an m by m and an n by n minus m matrix, and these n minus m x's we will make them equal to 0. So out of all the unknowns, we will take n minus m unknowns, make them equal to 0, and solve for the remaining m equations. And from that, we'll get one basic solution. One basic feasible solution, and we call that a basic feasible solution if this particular constraint is also satisfied. If all the x that you obtain by doing so are positive, then it will belong to the feasible region. Then you can call it a basic feasible solution. Of course, all the extreme points will belong to the feasible region, so all of them will be basic feasible solutions. This is just a way to tell you how to calculate the extreme points. So if someone gives you the extreme points, then it is straightforward. But the way the equations, you will be given ax in the form ax less than or equal to b. So from that form, or if you are given ax less than or equal to b, then you have to convert it into the standard form. Then you will get ax equal to b equation. And from this equation is where you have to determine the extreme points. And how do you get the extreme points is this way. So you decompose it, you take B to be a full row matrix, and then you decompose, and then you take an inverse, you calculate xp, and if that xp is greater than equal to 0, then that particular xp will be an extreme point. And you keep doing that for all possible combinations. How many combinations I can take? I can take NCM combinations. So for all those combinations, will be my extreme points. So once I get all the extreme points, then I can take the optimal value at each extreme point and see which one is the minimum. But obviously, we're not going to do that way. We'll further reduce our dimension. Like how can we, out of NCM combinations, how can we smartly select the ways? How can we actually use information from, say, I took a point. I know that it is not an optimum. Then instead of randomly selecting a next point, how can I use the information about at the current step? So at this particular point, I know that this particular point is not a solution. So what can I use from this information so that I can smartly choose the next point instead of randomly choosing some point? That is something that we will see later in sequence. So, and then we discuss a couple of problems. Most of these problems are whether it's a polytope or not, and then discuss about what a cone is, and then also what a recession cone is. And then we discuss problems on how an LP problem is, how many number of variables are required to solve an LP problem. And then we also understood why we don't need to have an unbounded, even with an unbounded problem. When my feasible region itself is unbounded, you can have an unbounded feasible region and still have a bounded optimal value. Like you have a finite optimal value. That can also happen. We have seen an example for that. And then we discussed on how if you have more than one optimal solution, then any convex combination of those optimal solutions will also be an optimal solution. Then we understood how to identify the number of whether a particular value will be a possible basic solution. Again, just to emphasize here, it's not just because 2 is not equal to 0. So maybe it should be better if I say that at least 2 elements should be 0. But I have only one. X prime has only one. Right? And then we understood how to find the number of possible feasible solutions, that is basically NCM combinations. And the last problem is where we check whether it is satisfies Ax equal to b constraint, and then also it has to satisfy x greater than equal to 0. Only when both of these are satisfied, it will be in the feasible region, and then you can call it as a basic solution, right? Yeah, these the quick summary of what I have discussed in this week. So, are there any questions? If there are no questions, then we can end the session for today. Thank you for joining. We'll meet again the same time in the next week. And also to those of you who have feedback form is also available to you, so you can fill in any feedback that you want. Maybe that you can change the type of problems or the way. If you do not understand any particular concept that I teach, I can reteach you again. Things like that you can put it in the feedback form, and then I'll get access to that. Yeah, that's it for mine. Thank you for joining. We'll meet next week again for the same time.